All right, so we're going to go straight into the next chapter, chapter 20 in the Klein textbook. And that's all about ketones and aldehydes. He lumps them together into one chapter because they have pretty similar reactivity for the most part. But before we get too far, let's talk about naming these. I'm not going to go into this in a whole lot of detail, but it does get kind of confusing, so I wanted to slow down and cover it. All right, so let's take the following molecule. Just like with any sort of organic compound, we want to identify the longest continuous carbon chain containing our functional group. And if I were to number this, would I number going left to right or right to left, do you think? Right to left. You want your functional group to be the lowest number. So I go 1, 2, 3, 4, 5, 6. So it looks like a hexane derivative, which means that our parent will start out with hex to indicate that there's 6 carbons. And then it'll be hexane-al. The al suffix is a suffix for any sort of aldehyde. Do we need to say one hexane-al? No, an aldehyde will by definition always be at the terminal end of a chain. So it's kind of redundant to say one hexane-al because it's implied that that's got to be position 1, right? So pretty simple. Let's try a harder one. And I want you to name this one. But check with your neighbor and see if you're right. So this would be an example problem on an exam. So longest continuous carbon chain would be what? 5. So we go 1, 2, 3, 4, 5. And then we would want to identify functional groups coming off, right? So over here we've got a methyl group. Over here we have a bromo group. What else should I identify? Stereocenters. So let's check this stereocenter right here for bromine. What would that be? Ooh, there's some disagreement. Check with your neighbor and see if you agree. All right, highest priority coming off that stereocenter would be what? Bromine. All right, so that'd be position 1. And then we've got to decide, will carbon 4 be higher priority or will carbon 2 be higher priority? 4. So we'll go 1, 2, 3. Carbon 2 has 2 hydrogens off of it, right? So it's a tiebreaker rule here. So we go around. To me, this looks like an R stereocenter. So now we can go ahead and start piecing this together. So we always put stereochemistry first in parentheses. And then what would come next, the bromo or the methyl? Bromo. So we could say R3 bromo, 4 methyl. And then what goes next? Pentanal. We don't need to write out one pentanol. It's implied, right? So just leave it as is. All right, so pretty straightforward with aldehydes. Ketones get a bit more complicated. All right, with ketones, we don't necessarily know which carbon they're going to be coming off of, so we need to be a little bit more careful. So in this ketone, we've got a continuous carbon chain. Should I number going right to left or left to right? Right to left, right? Because we want the ketone to be at the lowest possible number. If we numbered going left to right, the ketone would be at number 4 rather than number 3. Okay, so when we go to name this, we need to clearly indicate that that ketone is coming off of carbon 3, not off of carbon 2, right? So in order to do that, we would just put a 3 in front. But now we have a new suffix. This is the suffix for ketones. Does that make sense? So it's pretty systematic. You can also kind of treat this like how we treated alkenes, and you can say hexane 3-one. You might see that occasionally as well. So that 3 can be shuffled around. However, usually you see it at the beginning for simple ketones. Another system of naming this is one that most people don't normally use anymore. Somebody might call this ethyl propyl ketone. However, that's getting pretty old school. However, I will throw that out as being an option. So you see how we've got an ethyl group coming off one side and a propyl group coming off the other side. So you could call this ethyl propyl ketone. I normally don't like this naming system because it gets kind of confusing, especially if you've got substituents coming off of it. Normally the IUPAC system up above is way clearer for everybody. Does that make sense? So ketones are their own special class. We do have to number the double bond position. All right, there's a whole bunch of special ones that we do need to cover. So we'll do special aldehydes first. And what I mean by special is they're IUPAC accepted names, but not true systematic names. Yep, it's kind of like what we saw with our aromatic rings, right? When we talked about anisole rather than methoxybenzene, it's just an old school name that stuck around. All right, does anybody know what this one is? Formaldehyde? As opposed to casual aldehyde. I'm not even a dad, and I got dad jokes. All right. We got Benzaldehyde. And then the next one is a little bit weird. You will see this occasionally used in multiple ways. What would be the systematic name for this? So longest carbon chain would be 2 carbons, so it'd be ethanal, which just kind of sounds weird. So most people call this acetaldehyde.
Oh, that's so much better.
And that's because this is an aceto group, right? So acetaldehyde is how I pronounce it. Maybe I'm not even pronouncing it.
Where do you get that?
Oh, sorry. I am spelling that wrong. It's hard to write and talk at the same time. Like I said, though, you could call this ethanal. Both are perfectly acceptable, but most people would call it acetaldehyde. All right, next one. And this will be our last one. Be the cyclohexane derivative. This will be cyclohexane carbaldehyde. So kind of a little bit different there. All of these are IUPAC accepted, and you will likely run into them. All right, then we've got special ketones. All right, what's this ketone called? Acetone. If you were working in a lab and you say, can you hand me 2-propanone? People be like, wait, what? What's wrong with you? Call it acetone. It's a lot easier. All right. And then we've got this one, which we should all know. Acetophenone. So you can see the aceto group is used prominently. All right. And then last but not least, I think this was actually somebody's unknown for the NMR lab.
Yeah, I remember that.
Yep. Big blob of aromatic protons, and that was it. This is called benzophenone. Does that make sense? All of these have the ONE suffix, which is a dead giveaway that they've got to be some sort of ketone. Make sense? All right, the tricky thing is an area I tend not to get super heavy duty into, but it comes up when we get into these more advanced functional groups, and that's what if we have an alcohol and an aldehyde? Which one takes priority? It can be tricky. So the IUPAC committee actually got together and they created a list of the most important substituents going out to the least important substituents. This is kind of arbitrary. So a bunch of scientists came together and they just said, this is the way it's going to be. If you don't like it, leave. So the most important is carboxylic acids. So they'll always take priority over any other sort of substituent. And the suffix, we'll go over this later, is always going to be oic acid. For esters, the suffix will be O8. And if you, let's say, have a combination where you've got a carboxylic acid in one portion of your molecule and an ester in another, then you would call it an oxycarbonyl group. So it can be a little bit weird that way. So let's say we're down here and we're looking at the list. What's going to be a higher priority, an aldehyde or an alcohol? Aldehyde. So the alcohol would be referred to as a hydroxy substituent, right? So we do need to kind of switch things. If we have a substituent that we're used to taking priority, we may need to check a list and determine which one's higher priority than the other. Yep.
So, but earlier you had the ketone suffix be O.
Mm-hmm.
That's a different one.
So ketones have the suffix ONE.
That's aldehyde.
No, the name's under it.
Yes.
Oh.
Sorry. But I found this sheet on masterorganicchemistry.com. He has a really good set of explanations about all of this, but it's a really nice, concise sheet. You can tell down here the simplest ones are things like halogens and nitro groups. We always treat those as substituents. Then we've got the alkanes, alkynes, and all of those. It does get kind of complicated when you get into the double and triple bonds. Yep.
So when would you use carboxy if carboxylic acid always like the main one?
I think there are actually ones that are slightly higher priority than carboxylic acids. We're really not going to get into that though. Yeah. So let's take an example. Just so we can work through this together. So let's say I've got this molecule. All right, longest continuous carbon chain. We can number. What should be number one? Should it be on the ketone or the alcohol? The ketone. If you remember, we go back up here. Ketone is higher priority than an alcohol. So I'd put priority 1 there. Should I go clockwise or counterclockwise? Clockwise. All right, if we think about it, the ketone's higher priority, which means that this is going to be treated as a hydroxy group. And what's the stereocenter for carbon 2? It would be S. All right, so now we can go ahead and we can start naming this. We can say S, 2-hydroxy, cyclopentan, and then what would the suffix be? One. So S2-hydroxycyclopentanone. So like I said, I'll be the first to admit, when I run into complicated molecules, I'll pull up this sheet because I can never remember, is a ketone more important than an aldehyde or vice versa, or where's an ester in all of this? On a test, I will tend to make them fairly straightforward. I want to make sure you know basic naming. Yep. All right. Now that I've admitted my shame of not knowing how to name things, let's move on. Yeah, that's a good question. So the question was on the ACS exam. I think the naming on the ACS exam is very easy. And having process of elimination is a huge help. So oftentimes, because it's multiple choice, they'll give you names. You can even on scratch paper try to convert that name to a structure and see what matches the structure given. All right, so let's take a look at preparation of aldehydes, and this will all be review based on reactions we know. But I want you to help me find the reagent. So first one, what reagent would I need to accomplish this transformation? Not 9-BBN, that would be for an alkyne, PCC. So we could do PCC oxidation. If you want to go back and review, that's section 13.10 in the 3rd edition textbook, or 2nd edition, excuse me. And this only works for primary alcohols. Why won't it work for a secondary alcohol? You'll make a ketone, exactly. All right, next one. This could be a cis or a trans alkene. To an aldehyde, what reagent would I need here? So ozone, followed by DMS or zinc and water, some sort of weak reducing agent. And if you remember, we're cutting this down the middle, so what we're making is actually 2 equivalents of this, assuming those R groups are the same, right? This is going all the way back to section 9.11 in the 2nd edition. All right, and then the last one we saw worked with terminal alkynes. And we can make an aldehyde pretty easily this way. What reagent do we need? So if we did ozone and water, we'd make carboxylic acids, and we would have lost a carbon. What? 9-BBN. So we're going to do anti-Markovnikov hydration and oxidation. And so it's easy to miscount carbons. I like color coding them, right? So that red carbon is exactly where it was. And same thing with that green carbon down here. What if we wanted to make a ketone off of the red carbon? Yeah, we use our mercury 2 catalyst and sulfuric acid and water. All right, so this was covered in section 10.7. So all of these are review, but they are reactions you should remember from last term. All right. Similarly, we saw a lot of reactions where we prepared ketones. So let's go back and review those really quick. Whoop. All right, with ketones, kind of gave this away before. But if you have a secondary alcohol, we can oxidize this all the way to a ketone. And we said we could use PCC. That was a reagent we saw on the other page, so pyridinium chlorochromate, or what's the other reagent? Chromic acid. Na2Cr2O7 is sodium dichromate. You can make chromic acid by putting sodium dichromate and sulfuric acid and water. Either one of these reagents will work. All right. Similarly to what we just saw, we could have, in this case, a tetrasubstituted alkene. And we can make 2 equivalents of a ketone using ozone and DMS. It's the same idea as with making aldehydes. The big thing to remember with ozonolysis is you have to determine how substituted your alkene is before you can really determine whether or not you're making an aldehyde or a ketone. And then same thing with alkynes. We said that you could convert this alkyne to a ketone by treating it with sulfuric acid and water. And mercury 2 sulfate. Just like we saw before, it's now going to come off the more substituted position, not the less substituted position. Does it have to be a terminal alkyne in order to make a ketone? No. What's one problem, though, if we have an internal alkyne that's not terminal? We might get a mix of different ketones, so you do have to watch out for that. All right, and then last but not least, this term, we saw how we could convert benzene into an aromatic ketone. Through the Friedel-Crafts acylation reaction, where we need some sort of acid halide or anhydride in some cases, and react it with the Lewis acid catalyst. Make sense? So we've seen a lot of this chemistry already, just kind of in the scope of different chapters. All right, so now we get to get into the fun stuff, the new reactivity that we're going to address with ketones and aldehydes. And a lot of this is actually directly related to biochemistry. In fact, your problem of the day is looking at glucose, which is a biomolecule. So biomolecules like carbohydrates are really just fancy ketones and aldehydes. They just have a lot of alcohols hanging off of them. All right, so let's take a look at aldehydes first. And then we'll compare them to ketones. Okay, so let's just take a generic aldehyde and think about its resonance structure. Really only has one. Only resonance structure it has is where you kick up electrons onto that oxygen. Which means we would have a positive charge on the carbon and a negative charge on your oxygen. So this would be our aldehyde. And then we can compare this to the equivalent ketone. My question for you is, which one is less stable? The aldehyde? Why? So depending on your R groups, let's just assume that the R groups are, a normal alkyl group like an alkane. So somebody said more substituted carbocation on the ketone. So you see this carbocation where it has two R groups next to it that could stabilize it. How is it stabilizing that positive charge? Hyperconjugation, right? So over here, this is more stabilized. From hyperconjugation. Oh, can't spell. All right, so knowing that, which one's going to usually be more reactive, an aldehyde or a ketone? Aldehyde. They're less stable, therefore they're more reactive. And I'm going to put a usually under here because in chemistry there's always exceptions to the rule. So these are usually more reactive. And in this case, do you think an aldehyde's going to act as an electrophile or a nucleophile? Electrophile, right? When we saw Grignard reagents attacking, they attacked the carbon. In this case, the carbon's electron deficient. Therefore, the carbon's going to act as an electrophile. So it's less stable, and it's usually more reactive as an electrophile. There are weird exceptions. So for example, if you've got a ketone where both of these R groups are really, really, really electron withdrawn, you might actually see a ketone be more electrophilic, but those are more kind of the oddball cases, not the norm. All right, so aldehydes we know have a little bit more oomph to them. They tend to be a bit more reactive. All right, so let's see what happens with each of these when they're treated with a nucleophile. And a lot of these are pretty straightforward. So I'll just do a simple mechanism under basic conditions.
Just clarify, they're basic conditions as in like 8 to 14.
Yes.
Not just
Basic as in no acid.
Okay.
Yeah. All right, so let's take a look at an aldehyde because we know aldehydes are going to be a bit more reactive. If we have a nucleophile under basic conditions, chances are it's going to be a negatively charged nucleophile, right? So you can imagine this as a Grignard reagent, for example. A Grignard reagent's a really good nucleophile. It's never ever going to be under acidic conditions. And then what's going to happen? It's got to swing in, attack that partial positive on that carbon, and kick up electrons to that oxygen. Depending on the nucleophile, this may or may not be under equilibrium conditions. When it's a Grignard reagent, it's most definitely not equilibrium conditions, but other times it might be. And why do you think it might be under equilibrium conditions? How could it possibly do the reverse reaction? Yeah, if this nucleophile is also a good leaving group, it might be under equilibrium conditions where it goes in the reverse direction. So you do have to watch out for that. We know that carbons aren't a good leaving group, which is why with Grignard reactions, it's a one-way arrow, right? Because carbons are never a good leaving group. All right, so let's just kind of ignore that for right now. And then last but not least, what do we do in the final step for a Grignard reaction? We quench it with some sort of acid. However, we could even show this acid-base reaction as under equilibrium conditions because we're just making up some generic acid at this point. So there we go. Pretty simple reactivity. Big thing to remember is you can't have any acid around in solution for that first step, but you can for the second step. All right, another big thing to remember is about basic conditions. You want to avoid having intermediates. Actually, let me say organic intermediates. With positive charge. So you see how in this intermediate right here, I had a negative charge? I didn't have a positive charge. That's perfectly allowable under basic conditions. All right, let's take a look at what happens under acidic conditions. It's pretty similar, but there's a bit of small difference. All right, so let's say we've got our aldehyde around, but this time we've got our nucleophile. Oops, I should keep the equilibrium arrows. Got our nucleophile, and normally under acidic conditions, your nucleophiles don't have a negative charge, right? Because they're going to be protonated. So your nucleophile is probably going to be some sort of neutral species, not one with a negative charge, but in order to be a nucleophile, it's got to have some sort of electron density, so it normally has a lone pair. Make sense? All right, under acidic conditions, we also have acid floating around. So now we've got a decision to make. One would be to have your nucleophile attack in and kick up electrons, but what's the problem with that? Acid base is faster, right? That, and if we were to have the nucleophile attack in right away, we'd have an oxygen with a negative charge. That would be the same intermediate as we saw under basic conditions. So that's really just not going to happen in the first step. Instead, in the first step, acid-base chemistry is going to take precedence. We're going to protonate the carbonyl oxygen. We still have this nucleophile, floating around. That could be an alcohol, it could be a thiol, something like that. And then in this next step, now the nucleophile can add in. But at this point, the nucleophile likely has a positive charge, right? Because it started out neutral. So our final step should likely be what? Deprotonation. All right, same sort of note as before. So under acidic conditions, avoid organic intermediates. Oh my goodness, my hands are just giving up on me. With a negative charge. So up here we were able to avoid that by protonating in the first step. We had an intermediate with a positive charge, which is fine, but we never had an intermediate with a negative charge. So both of these intermediates had positive charges. Make sense? It's one of the most common mistakes I see students make is they always default to the basic mechanism because it looks a little bit easier. However, it is important to remember that it does depend whether or not it's done under acidic or basic conditions. All right, second thing. What do you notice about the acid here? It's catalytic, right? So the acid was regenerated, so we could make a note that the acid is often catalytic, meaning sometimes you only need a pin drop of acid around in order for this to occur. All right, the other thing too is when we started out, we didn't have any sort of stereochemistry to worry about. What did we notice at the end here? We've got a stereocenter. Do you think we're going to make exclusively R or exclusively S here? Nope, your nucleophile, when it attacks in, has zero preference, right? Because at this point, it's trigonal planar. It could attack from either face. It doesn't really have a strong desire. Yep?
What about the strength of the nucleophile?
So the strength of the nucleophile just impacts the overall equilibrium position usually. It could be a weak nucleophile like an alcohol and still work, no problem. Yep. All right, so we have made a new stereocenter. Usually it's racemic. There are some weird situations where it's not, but we do have to worry about stereochemistry. Does that make sense? All right, so let's make some more broad notes. I know there's a lot of notes with this one. All right, this is for both the acid catalyzed reaction and the basic reaction. First one is the reaction may be at equilibrium, especially if your nucleophile is an okay leaving group. Oops. If it's not a good leaving group like carbon, we know that it's not going to be under equilibrium conditions. All right, product can be favored a few different ways. So first thing you can do to favor your product is use a very unstable nucleophile. All right, second thing you can do is just flood the reaction with your nucleophile. basically have such a high concentration of nucleophile that it really has no choice. So sometimes we can avoid having a relatively stable nucleophile, but if we flood the reaction with the nucleophile, we can still kind of prod it along and get it to favor some of our product. All right. And then last but not least, aldehydes tend to favor nucleophilic addition more than ketones, which is exactly what we talked about at the start of the page. The relative partial positive charge on the carbon for an aldehyde isn't stabilized as much through hyperconjugation, so they tend to favor nucleophilic addition more. All right, so let's take a look at some common nucleophiles that are used in this nucleophilic addition. All right, so I kind of break these into a few different classes. We've got oxygen nucleophiles, we've got sulfur, we've got nitrogen, we've got hydrogen nucleophiles, and then last but not least, we've got carbon.
Don't rearrange the scale after you've already, because we can't do that on paper.
No, just pinch your paper. All right. So most common oxygen nucleophile on our planet is what? Water. So we could have water as a nucleophile. It's pretty common. All right. Next one we can have is the stronger nucleophile version. We could have hydroxide, right? So that might work for a basic condition. We could have alcohols, or we could have alkoxides. Both of those would work as well. And then the other one that's kind of cool that we'll talk more about tomorrow are diols. Diols are pretty neat. They can actually do this reaction multiple times. All right, sulfur. We could have hydrogen sulfide, although not super common because it tends to be super duper stinky. We could have thiols. We could have thiolates. Or we could have the sulfur analog of diols, right? So in this case, these would work. So this is also a kind of unique reaction using this as our nucleophile. We'll cover that later. All right, and then nitrogen. We could have an amine. Could have a secondary amine. Usually, though, we don't have the species where nitrogen has a negative charge. Why do you think that's a problem if nitrogen has a negative charge? Well, that and it might do other acid-base chemistry, because nitrogen, when it has a negative charge, is wickedly unstable and likes to do other sorts of chemistry. However, you might see it. So all of these might work if the corresponding atom has a negative charge. All right, hydrogen. How can we make hydrogen nucleophilic, meaning have a negative charge? Hydride. So what's our sources of hydride? We have two. So we had sodium borohydride. That's a source of hydride. And then if we really want to amp it up, we have lithium aluminum hydride, a much stronger source of hydride. All right. And then for carbon nucleophiles, we've seen a few.
Sodium hydride doesn't work at all.
So sodium hydride, if you remember way back to first term, I said is a good base but not a good nucleophile. Why? It's not soluble, right? So it'll do surface chemistry, but it's kind of a crummy nucleophile. All right, carbon nucleophiles. We could have Grignard reagents. We've seen that a lot already. So that R group essentially acts like a carbon with a negative charge, can attack into an aldehyde or a ketone. The other one, it's not as commonly used in our textbook, are cyanide anions, right? Because these can attack in, they're decent nucleophiles. What's one practical downside to working with cyanide? It tends to be highly toxic. So a lot of organic chemistry labs would prefer using this if possible, but you still see it used a fair amount. All right, and then, yeah.
Can you do alkyne?
Yeah, so are you talking about like an acetylide ion? I think you could. However, I don't think I've ever seen that. Actually, yeah, let's put that down. I'm going to put that down. Normally these are lithiates. So the counter anion would be lithium. Yeah, this would work. And then the last one that's pretty cool is one that we'll cover later. This is called the Wittig reagent. So we'll learn how to make these and their overall reactivity, but it's kind of neat. You can take a CO double bond and convert it to a CC double bond that way. So it's a new way of making carbon-carbon bonds. All right, that's where I'm going to end today. There are a couple more minutes left. What I would do, if I were you, is take a look at your pod. So if we look at the pod, glucose can exist in an open and closed chain form, which is exactly what this pod is about. So glucose in its open chain form is on the left. We've got an aldehyde. Ta-da! And then if we think about this aldehyde, right, this basically is the exact same molecule kind of folded in a different orientation. We've got this aldehyde right here. And we're under acidic conditions. And we've got a nucleophile right next door. What's our nucleophile? The OH group, right? Because over here we can clearly see we formed a new bond right here and right here, which means that this must be the alcohol that does the attacking. So what I want you to do is on the bottom here, draw the full mechanism for the ring closing reaction. Don't worry about stereochemistry too much. I just want to make sure you understand the overall mechanism and then complete the box question as well. Make sense? All right.